All right. So we need to start by defining a word here. The word is work. Okay. In physics, the definition of work is basically when you apply a force to an object and that object moves, work has been done. We have a formula that we'll have to use to calculate the amount of work being done. And you could probably guess its formula if you look at my definition. What do you think? Work equals Ryan?
W equals F over M, the mass.
Not quite, but you're getting there. Matt?
W equals F times M.
Not quite M, because the force you're applying is going to tell you the mass of the object. But you're right, work equals force times, what's the other factor we have to put here? No? Because we're applying a force, what's the object doing? Moving. So the other part is?
Velocity?
Not quite. The distance the object moves. So we multiply the force we're applying by the distance the object moves. So if I have my water bottle here, okay, for me to lift it, it requires some force. They actually tell you the amount of force using a spring scale. Spring scale measures the force. So if I hook my spring scale on, okay, for me to lift this, actually it's too big, too full. This only goes up to 2.5 newtons of force. This one goes to 5 newtons. So takes me 3.2 newtons of force to lift this water bottle. That is equivalent to 320 grams. Okay, so the amount of work that I'm going to do will depend on the force I'm applying, so I require 3.2 newtons, and how the distance it moves. So if I move it up this distance, I've done more work. Okay? If I just lift it a very small amount, I've done less work. So work equals the force you're applying times the distance that you have to apply it. So for example, if I push a box with 10 newtons of force and it moves 80 meters, okay, I can figure out the amount of work I've done pretty simply. And again, write our formula, we substitute our numbers, and we come up with our answer. Again, we're newtons times meters, not per meter, not slash meter. But we also have an abbreviated unit. 1 newton per meter is called a joule. So in this case, we've done 80 joules of work. A joule is a force it takes of 1 newton moving an object 1 meter. So if your units are newtons and meters, you know that's a joule.
Okay, so what if somebody spelled joule as J-E-W-E-L?
That would be wrong. This is named after a person whose last name was Joule. I mean,
Seth and I were learning about the last year. We used a spring scale, and he lifted it up and tilted it sideways because it was we were measuring a coke can full of water. He spilled out. So they had to measure everything.
yeah, the abbreviation is just a capital J for joules. All right, so a simple machine is basically a tool, an object that helps you to do your work in some way. But a key thing that you're always going to have to remember is that a simple machine does not allow you to do less work. It only changes how you do that work. So the amount of work done is the same whether you use a machine or whether you don't. And there's lots of types of simple machines that can do various things. They can transform energy from one form to another. They can transfer energy from one place to another. They multiply your force. They can change the speed of an object. They can change the direction of a force. They can do many things, but they do not allow you to do less work. And you'll see that clearly in a minute. All right, when we are using simple machines, we will be calculating what we call their mechanical advantage, abbreviated MA. Mechanical advantage basically tells you how much is this machine helping you. And we are going to have to calculate two different types of mechanical advantage. They're called ideal and actual mechanical advantage. Actual mechanical advantage, you could think of as sort of real life mechanical advantage, takes friction into account. It's how much the machine's actually going to help you if you were really using it. Ideal mechanical advantage does not take friction into account. It's sort of theoretically how much should this machine help if there were no friction. When we calculate actual mechanical advantage, we use the forces involved. When we calculate ideal mechanical advantage, we use distances. So, let's look at an example here. We look at this situation. You got it? All right. If I look at the situation, so I'll recreate up here with my water bottle. What type of simple machine is this? A lever. A lever, some might say. Okay. So, if this woman is lifting this rock off of the ground, rather than just lifting the rock off the ground, though, she's using a simple machine, a lever. Okay. So she's going to push down and exert some effort here, and that's going to lift the rock up. Okay. So, what kind of force is she going to have to use compared to just lifting the rock if she's using this machine?
She has to use an actual.
Well, what do you think? Is she going to have to use more force, less force? Less force. Okay? She doesn't have to use as much force. If I lift this water bottle here, okay, I can lift this I barely need to push on this lever to lift my water bottle. I'm using the same sort of machine that she's using, a lever. Now, if I want to calculate how much this machine is helping me, I need two pieces of information. The resistance force and the effort force, RF and EF. And I can probably figure out, what do you think the resistance force is? Think of resistance. Nicholas? It's the force of gravity pulling on what? What's the resistance? On the rock. Yes, it's basically, what force would I need to pick up the rock? So if I'm using my spring scale again, I already figured this out. What is the resistance force of my water bottle? 3.2 newtons is the weight of that rock. And what do you think effort force is?
How much effort?
Ryan?
How much force the person is exerting?
Yeah. how much force a person needs to apply to this machine to use it. Now what do you think? In my water bottle up here, it took 3.2 newtons of force to just lift it. What kind of force do you think I'm going to have to apply here? Around 1? It's going to be less?
Yeah, it's gonna be less.
Okay, so I can do that. I can use my spring scale if I click it on here.
I think it's gonna be
It's about 0.2 newtons of force.
what?
It only takes 0.2 newtons of force for me to lift up my water bottle. So I've used much less force with my machine versus just lifting it up like this. It takes a lot more force. All right, so if I want to calculate mechanical advantage, I could do that. I have the two numbers. Now, so in this case, resistance force is the rock, effort force is this girl pushing on it. Ideal mechanical advantage is the theoretical mechanical advantage, and it uses distances. So in this case, it's the effort distance divided by the resistance distance, ED over RD. Effort distance in this case is the distance I have to apply my force. And the resistance distance is the distance the object's actually going to move. Now it's important always to know that ideal mechanical advantage is always greater for a machine than the actual mechanical advantage.
How would you find the force?
Using a lever?
Yeah.
By using like some sort of spring scale that measures force. You know, if you hook it on and push on this tells you what force you're applying.
So that's what we're using.
Yes. All right. Now, before we move on, there's always a trade-off. A simple machine doesn't allow you to do less work. For me to lift this water bottle, I do the same amount of work whether I'm just lifting it straight or using this lever. There's a trade-off when you're using a machine. Okay? If I use this, so I can just lift it up, or I can exert a small force and lift it this way. But the trade-off is that I have to exert this effort to lift this water bottle just about, an inch off the ground. How much do I have to move this end of the lever? You have to move it a long distance here. I have to push all the way from up here all the way to down here. So I'm using less force, but I'm doing it for a longer distance. Okay? So that's always the trade-off with these machines. You can use less force, but you're going to have to do that for a greater distance. All right, and there's really, in terms of simple machines, we kind of list 6, but some of them are sort of versions of the other. And we're going to talk about inclined plane, wedge, screw, wheel and axle, pulley, and lever. All right, let's watch this quick video here, and then we'll start to talk about at least one of the simple machines.
Eureka.
Eureka! The story so far. Machines don't reduce the energy you need to move things, but they can reduce the force you need. They do this by increasing the distance through which you exert your force. The two simplest machines are the inclined plane and the lever. The principle of the lever states that the longer the arm of the lever to which force is applied, the less that force need be. And now, mechanical advantage and friction. Here are two scientists, Professor A and Professor B. They are both equally strong. And here is a very heavy book about science. We are now going to perform a scientific experiment. We are going to find out which of the two professors can lift the book with the lesser amount of force. First, Professor A. 24 newtons of force. Now, Professor B. Only, what, 6 newtons? Well, there's no doubt about it. Professor B is the winner. You're quite right. It's not fair. Professor B had an unfair advantage. He used a machine, a lever, to give himself a mechanical advantage, in fact. But just how much mechanical advantage did the lever give Professor B? It's easy to work out. Both professors lifted the book to a height of about 10 centimeters. Professor A lifted it straight up, so he had to pull against the full force of gravity, which was pulling the book down. But since Professor B's lever arm was 4 times as long as the arm the book was resting on, he only had to pull with 1/4 the amount of force, 6 newtons instead of 24. In other words, his input force was 6, and his output force was 24. And all you do to calculate the mechanical advantage of a machine is divide the output force by the input force. So Professor B's lever had a mechanical advantage of 4. You'd like us to repeat the experiment, Professor A? You think you can equal Professor B's feat of lifting the book with a force of only 6 newtons? Very well. Professor A is now setting an inclined plane against a block of wood 10 centimeters high. And the inclined plane is 40 centimeters long. Fine. That's 4 times the distance, so it should divide the force he needs by 4, which means that his Newton's spring scale should read 6.
Make it well?
What's this?
Why
8
not?
newtons? Well,
Friction.
there it is. Professor B is still the winner with a force of only 6 newtons, thanks to the mechanical advantage of 4 given him by his lever. Whereas with Professor A's inclined plane, we see that he has a mechanical advantage of only 3. Why is this? Why did the inclined plane have less mechanical advantage than the lever? Because of something we've forgotten about till now, the force of friction. Every time something rubs against something else, there's friction. In theory, Professor A should have been able to pull the book up the inclined plane with a force of only 6 newtons. But since friction was pulling in the opposite direction with a force of 2 newtons, the professor's pull had to total 8 newtons. Professor B, on the other hand, was lucky because the amount of friction between the point of the fulcrum and the lever arm is almost 0. So the lever is a more efficient machine than the inclined plane, because the inclined plane is plagued by the demon friction. But friction can be an angel as well, of course. Without friction between the tires of your car and the road, you wouldn't be able to run it. Or stop driving. Just as if there was no friction between the soles of your shoes and the floor.
Alright, so let's talk about one of these types of simple machines, the inclined plane, the ramp. If you walked into school today, the front entrance, you could get up from the sidewalk up into the door level one of 2 ways. There's 3 steps to get up, or what's the alternate way? The ramp. Okay? Now, the ramp is a type of inclined plane, So, what is the purpose of the ramp?
People who choose to go up and down.
Okay, yes, but more than that, what does the ramp do, Tom?
It makes it easier to get up. If
Yeah.
you're carrying something or.
Yeah, you have to use less force because the ramp is sort of a gradual slope. You don't need to exert a lot of force to walk up it. Whereas the stairs, you have to lift your foot, push yourself up 3 times. It's going to take a little more force. But what's the trade-off? Yeah. Yes. To go up the 3 stairs, okay, you need to go a short distance. To go up the ramp, what do you have to do? You have to go all the way out, loop around, come all the way back. So it's more gradual, but it's a greater distance. So less force, but greater distance. Where you have the stairs, okay, there's 3 steps. Again, that's a shorter inclined plane. What would it be like if there were no machine to help you get up there? No, the stairs aren't an inclined plane. Brandon?
We need to use 3 times the amount of force.
Right, but what would it look like if there was no simple machine to help you? Tom?
You have to just like jump up.
It'd just be like you have to like climb up the stairs like this. You have to get your foot way up there. And again, it's going to take more force, but very short distance. All right, that's how an inclined plane works. So here we have, stop.
I don't know.
We have a resistance of 30 kilograms, a box. Okay? And you could just lift it up 2 meters, put it on this desk. You could lift it up that way without using a machine. Or if I had from this desk a ramp, okay, could drag that box up to the same height. That's using the simple machine. Okay, so this allows you to lift an object with less force, but as always, you need to do this for a greater distance. All right, and now we can, let me ask you this question first. This isn't something I'll write down. How much work is being done to put that box up on that ledge?
15.
60 what? What is our abbreviation?
15 newtons.
Joules. 60 joules, we could say, of work are being done. Hold on. All right, so we can just put it up there. But when we use this simple machine, let's calculate its mechanical advantage. First, the ideal mechanical advantage. In a perfect world, without friction, what would the mechanical advantage of this inclined plane be? Tom?
It would just slide right up.
Okay, but you'd still have to exert a force to get it up there. What would its mechanical advantage be? How much should it help you, Nate? 4. Okay, the effort distance, the distance you're going to have to apply your effort is 4 meters, divided by the resistance distance, which is the actual distance the object moves in the direction you want it to go, for a mechanical advantage of what? 2. Now, what are our units? Tricky ones. No? Again, what you do to the numbers, you do to the units. Not meters.
Here's where.
I'm not multiplying meters times meters.
Meters divided by 2.
Meters by meters. What is anything divided by itself? The units cancel out. Mechanical advantage doesn't have a unit. It's just 2. Makes it twice as easy. Okay, let's look at the actual mechanical advantage now. So that's in a perfect world. But is there going to be some friction? Is it actually going to make it twice as easy? Not quite. So actual mechanical advantage, we use our forces. The resistance force, which is basically the weight of the object. What is it? 30 kilograms. Divided by the force you have to apply to use the machine. What is it? 16 kilograms. Giving us a mechanical advantage of 1.9. So it doesn't quite reach the ideal mechanical advantage because of friction. We see inclined planes all over the place. Steps are an inclined plane. Anytime you're going up steps, that's an inclined plane allowing you to use less force to reach a certain vertical height. These are the Spanish steps in Rome, Italy. Again, these very short steps like that make it very easy to walk up. You barely have to lift your leg to get up each step, but the trade-off, you have to go up a very long distance to get up to this height up here. Switchbacks. If you've, anybody run the development runs, the 10K development runs on Wednesday nights on the Parkway? Has anyone ever done that? Has anybody been in Valley View Golf Course, the switchback trails? Has anybody ever hiked Bald Mountain?
Yeah.
Okay. Does the trail up Bald Mountain start at the trailhead and just go up the mountain?
No.
Why not?
So that would be harder.
More force.
A lot more force. It's a very steep. What does the trail actually do? Goes, twists, comes back. Again, that's allowing you to get up to a very tall height, but by using less force. But again, the trade-off? To go up those switchbacks is a long distance to get to the top. It'd be much shorter just to go straight up. Okay? So again, that's an inclined plane. Okay, that's those switchbacks back and forth is an inclined plane. A ramp to move something up to a certain height is an inclined plane. The longer the ramp, the less force you're going to have to apply to drag this object up. But again, it's a longer distance. Yeah, Matt?
On the last on the slide before that,
Yep.
how did you get 2 for the ideal measure?
Because it's a 4-meter ramp
Yeah.
divided by 2 meters, which is the vertical distance. How far you're actually moving.
Oh, so like how far?
It moves in the direction you want it to get.
Oh, okay.
Is that?
Sophia? The 2 types of mechanical advantage?
Yeah.
No. One is sort of ideally in a perfect world, if there were no friction, how much would it help you?
No, but.
The other is, in real world, what does it actually do? Because you have to take friction into account. Kilograms.
Oh, I got it now. There's the weight of it.
Yes, that was the weight of the object. And that's also the force he has to apply. All right, any other questions about